Good morning. We are going to continue our course. Today is the second lecture, and we will focus on graphs and some algorithms of optimization. And we have a good fundamental basis for this. I will show it a bit later. Um, it will be maybe slightly more slow than the previous lecture. We will go step by step to through main algorithm, and I believe that it's very fundamental thing, and maybe you already know all this. But I think it's better to check because we have enough time to check every fundamental um, important theorem, and then slightly go to the more serious, well, more and more important applications. So um, I will give some description. Just to recall some ideas from the previous lecture, and then we will focus on the new things. Okay. Okay. I believe now you can see my screen. So, previous lecture was used to tell some basic ideas about rating, just very basic things, and we went through fundamental algorithm. Today we will discuss shortest path and some algorithms. Of, it's prim algorithm and other ones. They're very basic for this problem. We need shortest path and uh, spanning tree because we want to have some estimations for branch and bounds algorithm for traveling salesman. Traveling salesman has been chosen because we want to talk about roads, graph, logistics is very interesting here on graphs. And I uh, told some fresh ideas about game theory, um, logic, uncertainties, and I have shown several motivation and game theory optimization problems. How should we motivate people to do their work in a proper way here? And I've shown some ideas about activity, multi-agent systems, about equilibrium, some properties of equilibrium, uncertainties, and so on. Okay, the idea was to show. Okay, sorry. The the idea was to show you the large perspective um, to well create some interest to this course because motivation is very important always during um, your study. Okay. When we have this, we can go from the very beginning. We will recall what is graph, what is shortest path, and so on. Okay. So now we can begin. We can start our today's lecture. Um, this course was developed, partially developed, and its fundamental basic is based on course of Professor Boris Golden Goring. Um, he had his PhD in Netherlands, in University of Groningen. He also has his degrees in Russian universities. But also he had, well, it's not a very new course. As you can see, there is 29, 2010, so it's about 10 years ago. Um, and there are 20 lectures. We just pass through them, so we are not going to focus exactly on these lectures because we want to focus here for some maybe new, fresh ideas and maybe skip some things that are already well known because 10 years is a large interval. So, yeah, and it was developed on the Faculty of Economics and Business, and yeah, he was a professor on this course last year, maybe before this. Okay, and I will use it to show you. He has written this his lectures in the written form. I think I can share with you. But lectures has have some information that is too much for our course right now. We will cut off it. Um, but I will use some slides that mm, consists of information from his lecture. Uh, okay. Uh, his idea was to use, as you can see, algorithmic complexity, minimum spanning tree, shortest path problem, uh, transportation networks, and matching theory, assignment problem, traveling salesman problem, and so on. Uh, for us, it is very important that the focus is the last thing. So from the traveling salesman and further, so branch and bounds for symmetric, asymmetric, tolerance-based algorithm, and so on. We also we are going to add some new features from new books that I have mentioned at the previous lecture. Okay, so uh, we'll pass through all this material, but we're not going to stay here too long. Okay. Uh, it's very slow beginning. So if you just understand that it's maybe too hard for you, let me know. If you understand that it's realize that it's very slow, too slow, let me know. As I told before. Okay, combinatorial optimization deals with the problems of optimization, maximizing a real valued function. It's not always, so it's just a definition that is very useful for us because we can imagine a problem of combinatorial optimization when up to the function phi of x is not real valued. It's okay. It can be integers. But for our purpose, we can say that it's a real valued function. So there is just a definition for the certain purpose. Um, we can call function phi objective function, or as I told before, utility function and many payoff function for agents and so on. But objective, it shows that it's objective for us as a control center, control all of this. So it's our objective. Okay, there is a feasible region and a feasible solution. Feasible region is just some area, some set of possible variants, possible solutions that met restrictions. So we have restrictions and we have a set of possible solutions or feasible solutions. And we have a feasible solution It's a member of this set, an element of this set, and the idea and the problem how to find the member with the maximum or minimum of this function. It's a vector. There, um, you can easily imagine that many problems can be written as a combinatorial optimization. Why is it optimization? Okay, because we have to get the value of the function as much as we can, or maybe as less as we want. So it depends on our objective. For example, if we are talking about costs, we want costs to be very small. If we are talking about profits, we want profits to be very large. But it is not very big problem to convert one result to another. Um, yeah, it's very easy to show that if we want to maximize. Oh, sorry. If we want to maximize this one, we can define this one. And now we have a minimization problem. So it's not very uh, uh, big problem here. Okay. Yeah, and combinatorial. Yeah. Okay. Wait a minute. I have a question. I will check it. Sorry. Um. Okay. Can you send the lecture? Yeah. I did. I had not enough time to upload this lecture. Well, I have a lot of other things to do, but I will upload it on YouTube and share the links with you. And lectures, yeah, I will provide everything what I have, um, but I'm not sure that I could provide this OneNote material just because I'm not sure how to share this. I tried to um, get it into a PDF format, but it was not too successful. But I will try it again because it's just some very small problem. I don't think it's a very big problem software. So there is no bugs or some uh, big problems with that. So yeah, I will try to share with you. Okay. Um, okay. So the combinatorial means that we usually want um, to use some kind of brute force. So you have to check one variant, then another variant, then another variant. In general, we can't say that it's just an optimization. Sometimes combinatorial is just a word that doesn't give more sense for our problem because it's just optimization problem. That's okay. But combinatorial makes us think and use some specific algorithm for this. But we can say that it's optimization and so on. Usually, when we are talking about optimization, there are several problems or several tasks for us to solve. So its existence, if there is a solution uh, under such restrictions, uh, construction problems, can we get it? Because mathematics is famous for its existence theorems. So some mathematicians, they can prove that there is an optimal solution, but sometimes it is impossible to get in a constructive way this solution. So there is only a theorem that there is, but nobody knows where. It's very common in mathematics. But for computer scientists and for some mathematicians who like construction or constructive way, of thinking. For them, it's very important. They just reject use theorems if it is just an existing theorem. It should be a theorem, not only mm, existing theorem, but the theorem how to get this solution. Okay, there is enumeration, and enumeration makes this optimization problem combinatorial, because we have to check how many variants do we have here there. It's the connection of these problems, enumeration problems, is very tied to complexity of algorithms. So when we are talking about computer science, where we are talking databases and other things, it's very important to check the complexity of our algorithm. If we write perfect algorithm that will give us exact optimal solution, but it could take maybe 1 billion years. So what is the value of this algorithm? So maybe we need some heuristics that is maybe not so accurate, but we can get it in 5 minutes. Maybe it is better. So, but how could we get this information before we start our algorithm? We can check, we can try to enumerate, to solve an enumeration problem, and find how many variants we should check for its optimality, to be sure that it's optimal solution. Okay, and optimization problem, also if there are several possibilities, maybe we want to check which one is the best. When we have only one optimization function, as I told, objective function, it's not too difficult, because maybe it's not very important for us. We can get this solution or this solution. There is no problem. But sometimes when we have several functions, for example, one parameter is ecology, and another parameter is economics, and the third is safety, how could we compare them? So we can get the maximum of ecology, the maximum of profit, the maximum of safety. But what about combination? What kind of combination can we do? And it's such problem have their own name, like a multifactoring optimization or something. And there are several approaches. I don't think we will focus on them this time. So the optimization problem that we are going to solve are difficult, are hard enough for us to try to solve them. And we also can use an example assignment problem. I will tell about this problem a bit later. When we are talking about logistics, we usually use terms like graphs. Of course, logistics is not only graphs. We can imagine many problems in this area that is like assignment problem that is not connected to graphs. For example, assignment problem or task ordering or scheduling is not connected. They might be not connected to graphs at all. But graphs is something very special about logistics, so it's very interesting. When we are talking about logistics and other things, we have to use mathematical models. We want to use mathematical models. It makes our course and our knowledge quantitative. So we have to specify what does it mean, the transportation network of the city or transportation network of the country. we have to make some assumption on this, and we have a good variant for this is graph. So graph is just two sets, and that's all. The first set is the set of points or vertices. For example, it can be a set of cities, it can be a set of people, it can be a set of offices, universities, and so on, airports. And another set, which it is a age set. So age is just a pair. So we have to take that here, this one, the set of vertices. Then we can have edges. And age, what is age? For example, age is just a pair. This one, and larger than, for example, 10. And the second can be 5 by 2. It means like a vector in geometry. So we goes from the city V5 to the city V2. So it's like an age, but we won't use this arrow. Just say age. So it's just a set. So nothing more. We can use Cartesian product if you are familiar with this mathematics. So it's like we add ages. It's just a subset of Cartesian products. Okay, and we can say that graph, like here, graph is just vertices and edges. And that's all. We don't need to know colors, weather, cost functions. Sometimes we don't need them. Later, we will introduce cost functions and other things because it's rather important for us. Because when we are talking about logistics, we usually assume some economics or other things, social maybe effects. And here you can see figure 1.1, V1, V2, V3. So we have a set, so we can count them 1, 2, 3, 4, 5, 6, 12, and we have several ages there. Sometimes, well, in this situation, we can define ages like H1 and H2 the same. Well, we could try to do this, but when we are talking about sets, if this is the set of ages, then two elements, it's the same pair here. So it's just the same, they're equal. And we don't, well, there is a way of thinking in more general terms. For example, is hypergraphs and other very interesting things when we can get from one point to another point using several ages. But we also have sometimes situation when we have age this here, and we should have age on the in one side and back, and then we can just replace it by just an age from, well, not from, that is a connection between V and W, and so without arrows. But it's all about pairs here. Sometimes we can imagine a situation when we have pair like here uh, from the same point to the same point. Yeah, sometimes it is not allowed to do this, but there is usually not a problem to use them. Well, when we're talking about logistics, usually we should avoid such pairs, but it's not a problem if they are. Well, there are several special definition. For example, when we say K3 or K5, it means that we have a set of points, these points, elements, and the size of this set is 5, 3 here, and the set of edges is just this Cartesian products, so we have edges, but we don't use situation such that so we subtract minus here, we exclude them. Oh, sorry. Okay, it's some kind of cluster here, if, because every city is connected to every other city. If we want to talk about graph such that we can divide all points into two sets, large, to such that intersection is just empty, and their union just well, we can say that it's K2, 3. It's just some analog of cluster, because every point here is connected with every point, but not everywhere, only from another set. Okay, here it's just the definition here, but it's not K2, 3 or K4, 6, so it's not K4, 6, because we, for example, don't have an edge that is a connection from this vertex to this one. Why this could be important? When we we'll be talking about algorithms and some good ideas, sometimes they have some definition and some terms like if G is not K5, then, and so on. And if you don't know what does it mean, or if we have to describe every time the meaning of this term, it is not very convenient. It is not very smart. So it's just a short version. Okay. We will need a walk or road or something. It's just a situation. Just set, but it's more like a vector. So it's because it's set, we don't care about ordering. Usually we don't have to focus on ordering. We have to, if we want ordering, we have to describe it. It's not something that is included in set or ordered set, or partially ordered set. So we have used some words. So the walk here is some kind of ordering on elements. So we can say that this one is origin, and this one is a destination. Okay. And we can say that the walk is closed if we start from the one point and get to this point. So when origin was destination, it is told. Yeah. And it is very important for some algorithm that graph can be acyclic, so there is no cycle like this one. And if we don't have cycles in the graph, we have a special name for this graph. It's a tree or forest. Forest is just a combination of several trees. I will give you just basic idea. So the tree is like this one with one. It's a tree, and if we add more for tree here, sorry, like this one, now we have that this one is forest. Okay, and we can define equivalence relation. So on the on set of these points of vertices, so the relation R, it is very similar to the set of edges. So we can show the um, isomorphism or even the coincidence of this. But we can talk also about reflexive, symmetric, and transitive properties of this. So just reflexive means that if we have point, then we have h from this point to this point. It is not true for some cases. And symmetric means that I can get from point A to point B, then I can get from point B to point A. And transitive means that if I can get from point A to point B and from B to point C, then I can I get an H from A to C direct way. It is not always true. So many relations are not transitive. For example, if you are, well, maybe not. So many things are not transitive. Okay. And we can talk about a connected graph. It is also very important feature for some algorithm. So the connected means that I can get from one point to another, from any one point to any another point, using just edges. The walk from one edge to another. And each of these connected subgraphs, so subgraphs is just as well, if we have a graph here, we can say that this one is a subgraph of G if just a subset of yeah, okay, let it be, and ages subset of yeah, so it's a subgraph. Yeah, and we also Okay, have to check that we don't have here in F2 vertices from V that that are not members of V2. Special restriction on this, but it's very intuitive, so I don't think I should write it here. Okay, and there is a definition for component, connected subgraphs. So it's just a part. For example, if we have such graph, we have component here. This one is component, and this one is over 1, 2, 3 are connected components, or just components. Okay, I have described forest. What is forest? And it could be undirected tree. There are some equivalent definition of this. It's undirected. It's very interesting that if we know number of edges or vertices, and we know that it's a tree, so we know uh, how many. So if we know the power of v in a graph, we just know that it's a tree. This graph is a tree, and we know number of vertices. We can say something about number of edges, and if we know number of edges, we know something about vertices. Okay, there is some remark here. Okay, and what about spanning tree? Spanning tree is just non-directed tree with all vertices on connected graph. So if we have several points, then for example this one is a spanning tree. Okay, it could be a minimal spanning tree. If we assign some weights here, then we can say that if it is a minimum, and here is just an indicator of this age. If there is age, then this parameter is 1. If there is no such age, then we have this parameter equals 0. Of course, minimum is when we don't have ages at all, but spanning tree also requires that it should be component and without cycles. Well, it can be very easy shown that if there is no cycles, it's a tree for so if it is a tree and we know that it is one component, then there is no cycles. And back, if we have no cycles and we know that it's a component, connected component, then it's a tree or forest. Well, if it's component, then it's tree. Okay, when we will talk about complexity, we can talk about time complexity or memory complexity. There are many articles about that. But time complexity means how many operations should we do. And usually we assume that we have unlimited size of memory. That is not true in computer science, because usually we don't have unlimited amount of memory. But we can imagine that it's very, very large. And from the other side, we can say that it's memory complexity. So how much memory do we need for this algorithm, and so on. So, but usually we use time complexity and memory complexity. Sometimes we can use both of them. There is some estimations, and just I would like to recall that its course 10 years was developed 10 years ago. So when we are talking about seconds, steps, it's for old computers. It's not for the contemporary computers. Nowadays, our mobile phones may be faster than computers 10 years ago. So we have to check. But the idea is the same. So we have uh, here, it's just time complexity of algorithm A here, and the problem size S. What does it mean, the problem size? How can we measure this? It's just the number of parameters there. Usually, for example, it can be 10 variables or 20 variables, or maybe it's the size of our cluster. So it's some parameter that is very important for us to check how large is our problem, how large our transportation network in our city, how large is it city. Okay, and some ideas you can get in your Excel, for example. So if we have 2, 8, and 128, 1024, like cities, maybe offices, and then if we have algorithm that is just linear, n, the, its complexity is like an n, then it's not very large. But if we have factorial, for example, then we have very, 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 very large number. And that's why complexity does matter here. So if we have algorithm, maybe very difficult to understand, but if he gives us this cost of time, it can give us only this one. Well, that is just this number. Or we can write down, develop a software with just brute force that is very easy to understand, but it's not very effective. And in this case, if complexity is factorial, then just for s about 1000, we have very, very large number of all operations. Okay. Assignment problem, we will talk about it later. Just the problem how we can assign a worker to a work. So who should do what, and we have costs for them. So one worker is specialized on task 1 and 2. The third worker is his specialization is task 1, 3, and 5, and we have a certain times for him to make this work. So sometimes we have to choose what is the best assignment. And if we are talking about 5 workers, possible assignments at about 100. But when we're talking about 20, so we just have 20, 20 tasks somehow. Oh, similar. And we have 20 workers, and we have to assign them. It takes a very large number of variants, and it's not very easy even to save it in memory, because we need, for example, it's bytes or just bits. So still very large. 18 zeros, and it's only for 20 workers. Not so it's not so large amount of workers. So if we have a factory or some logistics like mm, Uber or other company, it's much larger amount here, not 20 definitely. And here we have a lot of variance for assignment. There are a lot of heuristics there, so don't worry, they have very, very good solution. But if you want to check every possible way, it takes a lot of time. Okay. Uh, there is a Hungarian algorithm. Maybe we will discuss it today, or maybe next lecture we will use to discuss this algorithm. But if you want to solve this assignment problem just by mm, complete enumeration, or we can use algorithm, special algorithm, and we can see that the difference is very large. So why people they focus on algorithm is just the complexity. So the one software company he tries to recognize a face, or maybe to make routing like Cisco, or maybe Huawei. I don't know any other company. They can write very simple, just complete enumeration algorithm, and it will take a lot of time to complete this algorithm. So it's not possible to use it. And on the other side, there is an algorithm that is very fast here. And maybe today we will talk about this algorithm too. So it is one of the ways to solve an enumeration problem, assignment problem. Sorry. Okay. And when we talk about logistics, as I told, so vertexes is cities, E just pairs of these cities that are ages here, and transportation or communication networks is just a graph. And we have some notion here, so we can say that. Oh, sorry. N is the number of cities, and M is the number of ages for the simplicity. We can say that 2 points, 2 vertices V and U and V are adjacent if this condition holds. Okay, and also ages, adjacency relations, incidence relations. Sorry, and that's all here. Okay, and usually we will talk about simple graphs. What do we mean when we are talking about simple graphs? It's not the common sense definition, because we can think that this one is simple, my subjective opinion, and this one is not very simple, and so on. But there is a special mathematical definition for simple graphs. There should be no loops or parallel edges. Okay, parallel edges means not that A, B, and C, D. It's not parallel edges. Well, in the usual sense, no. Parallel edges is this one. this one parallel edges. Okay, sorry. And we can say about a regular graph, if every point have the same number of edges, it can be not a symmetric one. Let's just imagine that we have, it's a model of social networks. So let me start from this form. So we have 6 cities and several edges, and for them we have 1, 2, 3, 4, 4 for adjacent vertices, but then it's the model of sorry here. It's a model of what's steroids. We take it and then we rewrite. So we eliminate one edge here, and we eliminate one edge here, and we rewrite this one to this one and this one to, oh, sorry, they already had. Okay, but if they had no such direct, it can be such rewriting. As you can see, the number of adjacent points holds, so there is no difference, but we have non-symmetric graph here. Well, we don't have, but we can have non-symmetric if we want to. So it can be a bipartite graph. I told about it. There was an illustration for this. If you have several edges, and we can say that we can divide it, these edges, into 2 sets, such that there is no connection between these sets, between these members of each set. Only only connection where the first city is a member of one set and the second from another set, like here. Okay, it is bipartite graph, and it can be complete bipartite graph if we have, if any city from the vertex 1 is connected to every city from the set 2. Okay, we can say that there is a subgraph. I told you about this before. So it's like we have graph, for example, this one, and we want to have subgraph. Okay, no problem. We can take this edge, this edge, this edge, and several vertices here. And this green graph is a subgraph. Okay, and this one that is larger is not only a subgraph, but it's a spanning subgraph, spanning tree. Okay. So we can say that a subgraph induced if we just fix several edges and we hold all, well, edges, points, vertices, and we hold all edges between them. Okay. And the shortest spanning tree is just we need a special function L, so length of age 1, for example. It just costs to get from one point to another point, and we can say that a tree is the shortest spanning tree if it is the component and it's a tree, no forest, just a tree, and it's yeah, and it's tree, and shortest means that the sum of such costs of edges is the minimum. Um, okay, well, it should be this one. L. If L is a function of distance and E is just an age that is taken into this our spanning tree, so maybe some vertices, some maybe not vertices but edges we don't want to take, so we exclude this one. So this is the spanning tree, and we have special notation SST. And this problem, sorry, is a combinatorial optimization problem, and we have just to find the minimum of t, where t is 3, such that this L of 3 is the smallest. So, and the definition of t of L of t is this one. So when we are talking about age is just a distance, but when we are talking about where t is not an age but a graph, so in this case the cost is just a sum of costs, of smaller costs. Okay, so it can be applied to roads, gas pipelines, electric power lines, and so on. Why is it important, for example, for gas or oil? Because we don't want to pay additional cost if we can get from country A to country B, and from country B to country C. Why do we need H from A to C? No, it is very expensive to have this because we can get from A to C not directly but through B, and it's enough. So it's not a problem to transport from A to C. Sorry. Okay. And there is some remarks of this. How can we get this tree? We will talk about two algorithms. So the first greedy and the second greedy as well, Kruskal algorithm, and the next one is prime algorithm for constructing. There is a description, but the main idea is that we take a graph and initial graph, and we have a special graph. It's now a tree, spanning tree, and we will take some. It has the same number of edges of vertices as our initial graph, and already a subset of edges. So we can, for example, here. Sorry. Okay. Here we have graph, but if we want to have SST, is just maybe this one. Not this one here, and not wait, this. This is shortest if we have special uh, cost functions here of there's a distance, but maybe it's just maybe not short, but just of course it's just a spanning tree. It's okay. If we don't have costs, we can construct just a tree and that's all. But if we have requirements to have it the shortest way, so we have to compare just distance. It's okay. Yeah, and the algorithm, eh, so it's the input, this is output. We are looking for an age, the shortest age. So we check if there is a short, and the shortest. Okay, maybe this one is the shortest. And we say that, okay, this age will go to this set. It's okay. But then we check if we next one, maybe this one. Okay, we add this one. The only restriction that you can get this one, no problem. But the restriction is that we cannot add a age if uh, it gives us a cycle. So we cannot add this one. No, here, even if it is very short but larger than the previous ages, we cannot add it just because we want to avoid cycles. So it's very important that cycles is prohibited here. Okay, and this is a Kruskal algorithm. Description. If we do this, we will have it's a proposition here that the result of this algorithm is just a spanning tree. It is not funny, but it's a property of this algorithm that if we have not several not connected cases, like here, here subset or subgraphs, say graph one, this one, graph two, then we still can use Kruskal algorithm, no problem. We just check ages and check if there is a cycle and so on. So it's not a, it should be, there is no requirement for these elements to be in a component, in a single component. If we want to create such a spanning shortest path, shortest spanning tree in a social network, it is very common situation when we have a social network, and we have component, very large component, maybe it's 90%, but we have many smaller one. And we have the same for the transportation networks. Um, Sometimes we think that we can get from one point to another point, but we can, for example, consider only airplanes and only flights. And then we can get that it is very difficult to get from one point to another only by airplanes. Maybe there is no connection because we have their trains, or maybe we have roads, and we can get from one point to another by cars, helicopters, even so, not by airplanes. And so, but Kruskal algorithm is still valid. Okay, some information about it, and yeah, another one is a prim algorithm here. As you can see, it is very old. When we are talking about science in general, like mechanics or maybe Newton laws, or maybe even logic like Aristotle logic or Socrates logic. Uh, its history about 1,000 to 2,000 years, so it's very ancient. Science of, or if you want to think about science of pyramids or Great Wall in China, so when engineers used science, it was long time ago. But when we are talking about computer science, when we are talking about software, algorithm, and other things, just 100 years is a very long time. You can easily see that uh, any update of telephones is maybe not every, but every year we have faster and faster our phones, and fast and fast. It's not only because of the processors, but also because of algorithm. So this one is rather old one, but it's basic. It's fundamental. It's what people have invented, and it's optimal because it's very fast, and it can be easily implemented in software. So it's very basic thing. But what is the prim algorithm? So we have, yeah, we have time before the break, before the pause. Uh, a prim algorithm is something different. It's also greedy. Well, when we are talking about greedy algorithm in computer science, what does it mean? uh, do they have emotions or greedy? Is a philosophical thing? No, it's not about philosophy or ethics. No, at all. Greedy means that just algorithm try to locally take the variant that is the best in the local sense. For example, I don't know. Uh, I can do just whatever I want, and I think that I'm greedy. I don't want to wait for an hour, or I don't want to wait for a year. I just want to get maximal profit right now. And of course, if it is not optimal solution. For example, mm, I want money. Okay, money. So and I want to steal something. Well, locally I will have money, but later I will go to jail. So from the strategical thinking, it's not an optimal solution. So if I don't want to go to jail where I don't have much money, I shouldn't steal. But greedy means that I want to have money as fast as I can. As you can see on this example, it's not optimal solution. But sometimes, and it's a theorem that greedy algorithm is good enough. It can give us the best solution sometimes. Uh, I don't know. Maybe if I want to win just Olympic Games, I should try to win at every tournament, and by this way I can get to the Olympic Games and win Olympic Games, and I can be a champion there, and the number of gold medals will be the largest. But yeah, and it's greedy, this algorithm. So there's no problem in computer science with greedy, but we have just to be careful that it's far from being always optimal. Here is there are two algorithm, greedy algorithm, Kruskal and uh, a pri, pri, prim, prim, I think. Yeah, and they're very optimal. Well, not very, but just optimal, and they're fast. When I talk about uh, complexity of fast or not fast algorithm, I mean that okay, if we don't have such algorithm, what is the way or what is the brute force to get the solution? Well, we have to list all possible trees, a lot of them, and then just check the our objective function value for each of them, and then compare. but it will take a lot of time. So this algorithm, a greedy algorithm, give us a big economy in the terms of time. Okay, and there is, yeah, and what is the prime algorithm? There will be a description, formal description, but I would like to give you a basic idea of this algorithm. So the idea is that if we have a tree, so let's imagine that we have a dotted line is just a age of initial graph, and let us imagine that we are at step 5, or it's because we have 1, 2, 3, 4, 5, 6. Oh, well, it's step 6, and we have chosen that we use this age, this age, this age, and this age, and this age, and we don't use, for example, this age, and we want to connect to this graph these vertices. If we are going to use Kruskal algorithm, we have to find here somewhere age with the shortest property, shortest distance property, and then check if there is a cycle, and then take or not take. But for a prim algorithm, there is another idea. We take just one city, 1 point outside of this graph, and check what is the shortest connection, what is the shortest distance to all other um, points. And then we find this, for example, the shortest is this one, and we connect here. And we also have to check if there is a cycle. So we should check only those where there is no cycle. So this there is no cycle, and let's this age is the shortest, and so on. We check this one, this one, this one. The important thing that it doesn't work for disconnected components. Uh, for Kruskal algorithm, there is no problem. We can get spanning tree as a spanning forest, for example. So, but here no, because we have some tree and we add to this tree, and if we have several cities, they are not connected at all, no connection with them, so it doesn't work. So we can't find the minimal, the shortest path here, because there is no such age at all. So no age, no no minimum of this. There is an example here. I would like, well, we just pass through. We won't analyze it right now. We have only 7 minutes before the break, and just not so much important. It is in lectures, and we can see that there is a difference between Kruskal and Prim algorithm. There's just many details here. Maybe later, if you have questions, or maybe during another lecture where we would like to focus on, especially on examples, on solution, we'll focus on this example. But right now, just uh, several ideas I would like to share. The first one, what is this magic? So the first idea that we were talking about set of vertices and edges, and we drew some pictures. But what about this matrix? Is there any connection? Yeah, there is a connection, and this thing here, so we can denote it A, G, and this is just the length of age E, that E here, like J, yes, from VI to VJ here. Or it can be rewritten like distance from VI, VG. Or if you have enumeration like here, AG is just L for pair A, G. So we can construct a matrix. The only problem if how should we denote situation when we have no path through between two vertices. So, for example, here and here there is no edge. So what should we place there? So there is no such L, no such. So it's like a L of empty set. Well, sorry, there is no. But we have some definition for this notation. We say that it's just an infinity. Of course, when we say about infinity, we mean not just minus infinity, plus infinity. We mean this one, plus infinity. And here we are talking about costs. So yeah, if there is an h and here we have infinity, so we never get from A to B. Never. Well, we, because this one, for example, is well, if it is time, then never. If it is cost, then we can get from A to B, but we have to pay infinitely large costs. Well, I'm not sure that it's possible, but mathematics is a difficult thing. So I can imagine that it can be possible in some settings. Okay, and there could be graph here. Just this is not a value, but there are problems when this vertices has its value. For example, its amount of citizens of this city, and we have a travel salesman problem, maybe not the classical one, and he wants to visit cities, and the value of the city depends on the number of citizens. So, but here is just a number, so just one, two, could be I, J. It's not a value, and age here, as you can see here, just a graph. An example of spanning a tree here. Another spanning tree. Well, it's just a checking of cycles. Let's imagine that we have an initial graph here, and we want to check what should we do. So let's imagine that we don't have this one and this one. Well, we have them in initial, but we have to check which one should be in our spanning tree. So we cannot add both of them because there is a cycle here. And if we take it here, it's not allowed, so we have to choose which one. And we can check it by the comparing distances. Well, okay, we will go to pause, maybe to break for 20 minutes. We have a shuttle here, and we will be back at 11:10, and we will start from the very interesting problem. I believe it is unsolved right now. I don't know any solution for this. Maybe it is already solved, but I don't think so. It looks like it was very difficult problem just several years ago, and I had no news about it. That Stein problem is solved. Okay, I have alarm. Okay, so see you in 20 minutes. If you have questions or some ideas, remarks, comments, please let me know at 11:10. Okay, it's 10 past 11, and we can continue. Steiner, well, we were talking about a prime, prim algorithm, and another one that is, sorry, I don't remember spelling. It's Kruskal algorithm, or Kruskal. I'm not sure, unfortunately. Skull. Both greedy and optimal there. Well, I would like to show one more greedy algorithm that is okay. It could be very interesting and important when we are talking about okay, yeah, when we are talking about gradient method that can be used somehow in neural networks or another optimization thing. So we just if we have function and we find point, then we want to go to another point, and in what direction. So we can make a small step if we have that. Well, here, but for example, it should be here, 0. It's a vector, so and this one can be just the direction and just a derivative of well, it's just a gradient of f. It's a vector, and we multiply by a small step, and it's some kind of greedy one. Yeah, because we go straight to the minimum or maximum locally, and there is a problem with this algorithm, with the gradient method, that we can jump through. We can pass through the minimum, real minimum, if our step is too large here. Now, there are many other problems, but gradient method is some kind of greedy one. Okay, the Euclidean Steiner problem is a very elegant one. It looks very easy. Well, not very interesting. So the idea is, okay, let we have, and it looks like a very practical one, but it's a very difficult one. Okay, we have cities. I don't know, maybe 4 cities. City A, city B, city C, city D. And we have roads. This one, this one, this one. Okay, nice. Well, and we think that this distance is just the Euclidean distance. So we can have coordinates here. It can be something similar to for airplanes here. So it's just for flights. Or some other ideas. Or maybe it's just in desert. So when we have a plane here, okay. But then, like in Russia and in many regions, these roads become very too old, and we have to choose if we want to repair them or to construct new one. And we would like to consider new roads. Maybe these ages are not the best to connect all these cities. And if we are not talking about airports, because we have to create airport, it's very expensive. But maybe sometimes we should. The idea is that we are allowed here to make some points, and it's like we add some points in some elements in our vertices set, and it looks like here and here. And it could be that it might be that the distance of green lines, the sum of these distances is less than the sum of violet uh, distances. Sometimes it's not the case, but sometimes it is the case. And the problem is to check if there is such rows here. And okay, if we know where we should place these points, then we can use our Kruskal algorithm or Prim algorithm and find the spanning tree, shortest spanning tree, and it's okay, it's very effective. But the problem is, where should we place them? Here, or maybe here, or maybe here, and how many points should we place here? Maybe 3, maybe 1, maybe 2, who knows? And we have to find them, and it's not very easy. Well, we can, of course, create a neural network. We can create optimization, universal optimization. We have algorithm for Steiner problem, of course, some of them. Uh, but I cannot just directly show you the way how to do this, because it can be 5 points here. Of course, we can try branch and bounds algorithm and other approaches, heuristics, and so on. But it is not very easy to find. Okay, I mean, analytically, not just using uh, approximation. Approximation is okay, but when we want to find the uh, a distinct value, for example, maybe the coordinate of this point is just p and p in the power of e, and we want to find the exact solution, and this is the problem. If you want just approximation, it's much easier. Okay, it's a Steiner problem, or Euclidean Steiner points. Um, when we are talking about a D-graph, it's a one-way relationship. It's just a set and another set, and there is, well, the graph means that we have not sorry, not just age, but the directed age. And this is the idea. The difference is important, though. A definition I gave before is for D graph, as you know, because it's pair. So it's more about D graphs. But those algorithms are for graphs. So graphs is just the special type of D graphs when we have a symmetric property, and that's all. Okay, but in a D graph we have directed walk, directed path, directed cycle, and so on. For example, this one is cycle, but this one doesn't look like a cycle. Okay, and there is a strongly connected, and there is a spanning tree, branching, and so on. There are some properties of this. Okay, and so we can say that we want the shortest path problem for the D graph. So there is a L function from edges or arcs into real values. So R just real values here is dimension. Yeah, arc. So there are weights, and we want to find path, shortest path problem. Okay. I think we can skip it right now. So there are some results, but it's not in our focus today. Maybe later. I just show the algorithm of it. It has very relax name, relax CPA, or in Russian SPA. Yeah, the first step is initialization. Then we have the second step and the third, and that's all. And the theorem that this algorithm really can really give us the shortest path. There is an induction. I will skip it. And I would like to focus a bit on this estimation. What does it mean? Of course, I suggest, well, I suppose, I assume that you know these things, but maybe not. And if not, it's a good time to talk about this. So it's just a notation to say that this function is grows not as fast as n in power of 2, for example. If we have a function like n in power of 2, then we can say that f has this property of equals if it grows not so fast. It can be, for example, it can be this one or this one. So it is important. Well, this one is exact thing. So we imagine when we usually write it, we mean that it's maybe smaller, but not so much, because you can say that it's not. But for example, n, if it grows very, very slow, so we can write this one instead of this one. But so usually we mean that our function is some polynomial of this power here. But the idea is that it's not always, well, if we have one algorithm with complexity this and one algorithm with complexity this, if n goes to infinity, plus infinity, this algorithm is worth just because it takes too much time, too much operation. But it doesn't mean that if n, for example, less than 100 or even 1 million, then this algorithm is better. Sometimes no. Well, this algorithm is better. Sometimes no, because the coefficient here may be very small. So we can have, for example, 0, 0, 0, 1, and n, well, n square, and we can have this algorithm. Costs here and here. We know that in when n is large enough, this one, these costs here are larger, just because of this square. But when n is rather small, then these costs are higher. So we should be very careful about this complexity. So if for real application, maybe this algorithm is not so good. And we have, well, we do not know several algorithms that are proved to be the optimal. Well, they have the best such estimation, but they're never used in real life because they have too large this coefficient. Okay, but for theoretical purposes, we usually assume that the larger function here, the worth algorithm, the algorithm. So there is the proof. Well, n square looks like a very good thing, but sometimes even polynomial is not very good, and sometimes we're looking for algorithm like n log n. For example, if we have n like 1 billion, then 1 billion in the power of 2 is much greater than 1 billion multiplies logarithm of 1 billion, because it's very small number. If we compare it to 1 billion. Okay, it's just some notions, some remarks. I hope you know them, but it's better to check. Okay, and there is a time complexity here, so it's proved. There is also a Bell-Montfort shortest path algorithm, BFA. Here, you can find it in this lecture when we will look through. So there is just a special function to find the minimum of minimum and so on. It's very, it's not very easy just to do, but it's very easy to implement in the software. So, and the theorem is very short. Oh, sorry, that this one is correct. So it provides us with the shortest path, some proof. We will skip it. Okay. Sometimes people use linear programming implementations that can solve shortest path problems. Linear programming usually means that we have like, sorry, some restrictions, and we have linear linear objective function. In some cases, yeah, and we have to find such x1, x2, and so on, that these restrictions like b1 and so on are met, and we can maximize or minimize this linear function. There are a lot of algorithms for this task, and so it is. The very important is I don't remember. Yeah, I had an article about this topic, but I forgot the name. Yeah, simplex method. Yeah, simplex method. And we know that in average algorithm that can solve this system is like a linear. It's just like this on average. But for the worst case is it's like an NP-hard problem, as I remember. But on average, it's okay with this problems. And there is also the problem with convex area. If we don't have a convex area here, the problem complicates. So, okay. But you can use it. And the good thing about this linear programming is that you have in almost any language, scientific language like MATLAB, R, Python, and many others, special functions to find the solution for these linear programming problems. Mathematica, for example, from Mathematicas. I would like to show you a very, I think, easy way. It's a Dijkstra algorithm. It's my favorite one from my school time. Algorithm, because it's very intuitive. Let's imagine that we have a graph. We have some posts here. It can be directed graph, no problem. So D graph, or it can be no D graph. It's no problem as well. We want to get to find the shortest path from this point to, for example, this point or any other point. What should we use? How should we find a way from A to B? For example, we can have here. So should we go here, or maybe this way, or any other way? And he found long time ago the way how to compute it. And the good thing is that we can get as in just additional benefit as a bonus the shortest path to from A to any other to all other points. The idea is very simple. So we want to check. Wait a minute. We want to check. So how can we get to the closest, to the most close points from A? Here and here, let it be alpha, beta, for example, and we place here this H or at this vertices these values. It's cost, so time that is required to get from A to this point. Okay, we have it, no problem. Then we check all vertices that are connected with this vertex. Oh, this one. We can check. And in case if we have a point that is connected to two or more vertices that are already marked, we check what is greater, the mark at this point plus this sum, for example, gamma and delta. What is greater, beta plus gamma or alpha plus delta? And if this one is greater and we want to find the shortest path, we can use this one from A to here because it's the shortest one, and we place here just alpha plus delta because it's less than this one. Okay, and we do this for all vertices. Another name for this algorithm is a wave algorithm, or maybe other names. And we get it from one point to another, and we comes to this point, to B, and the name that and the number that we place at B will be the length of the shortest path, and we can find the path itself. So we just have to go from A to B, always choosing the shortest path. Well, maybe not the shortest. Yeah, I'm not sure it's a greedy algorithm. We have to mark such edges. For example, we shouldn't mark this because it's not the shortest path from this point to this point. We know it's it may be a short path from this point to this point, but when we want to get from A to this point, we should use another way. So that's why this one is not important for us, and we can. And then if we have such a tree, it's a spanning tree. Yeah, it's a spanning tree. Uh, yeah, it should be. Then we can get to this. Okay. Yeah, and I would like to emphasize that it was invented long time ago. There is a label. I referred as marks, but labels. There is some explanation, and there is an algorithm. You can look at this and then find the solution. But and only 3 steps. As you can see, for prim algorithm, for the extra algorithm and all other algorithm here, we have just 3 steps, 4 steps, no more. They're, in this sense, they're very simple. If you want to write it, the problem of implementation of this algorithm sometimes not this algorithm, but a similar algorithm when we have 3 steps and 4 steps, just 3 or 4 steps. If we want to make a parallel version, so let's imagine that we want to create a program and we have a lot of cores and we don't have automated way of paralleling. So like we have bought a Tesla, I mean, not car, but a special video card, GeForce, and so on. And we want to use their processors, graphic processors, to improve the efficiency of our algorithm. And we want to use their parallel versions, and we have to implement this algorithm in a parallel version. And sometimes it's not very easy, sometimes it's very easy. For example, in some cases, prim algorithm and other greedy algorithm, it can be used. But I'm not sure that I know right now directly how to write it, this parallel version of this algorithm. Okay, and yeah, and of course the problem it's a bit another problem that if we have some probabilities and if we don't know exact values of these distances or costs, we have some kind of probability, and it's a much more difficult problem to find this. But it was I have discussed I have told about it at a previous lecture. So this time I would like to skip this basically, and maybe next lecture we will come back and we will combine, or maybe not next lecture, but next lecture. Now we are going to discuss the assignment problem. This problem is not maybe as hard as I mean intuitively as hard as as problems with graphs, because there is indeed no such graph here. But we can imagine it's not very uh, difficult such connection between assignment problem and such short spanning tree and other algorithm. We will talk about this later, I think. I have several slides, uh, but we can find some restrictions for assignment problem, and that will make it very difficult. But anyway, it's very hard still. It looks very simple, but it's not. Okay, And there is a proposition that we can subtract if we have a matrix of assignment. And that is very interesting that we have a Hungarian algorithm for solving assignment problem here. I would like to share it with you. Input. So we have matrix n and we have n workers and we have n jobs, and we want to assign worker to a job. Worker to a job. There are many variants. As you can see, it's a permutation. I just recall that permutation. We have, for example, we have jobs 1, 2, 3, and we have workers A, B, C. So we can assign A to 1, B to 2, C to 3, but we can assign B to 1, C to 2, and A to 3, and so on. And number, if we have just n of them, and here, n factorial. It's very easy, can be proven, because we have only n variants for A. N variants for the first job. We can choose any of them. When we choose one, we have only n minus 1 free workers, which we can choose for B for the second job, and so on. So it's a n factorial. That is, and so okay. And output here is just a permutation. So this is the set of all permutations. That is very large, and we need. Well, I would like to recall that it's not very small. This one grows very, very, very fast. For example, there is like here just one estimation. I don't remember this theorem, the name of this theorem. It can be proven by induction, but you can see that here we have n in power of 10. Well, n is divided by 3 in power of 10, but it's still very large. Okay, output, yeah, but we need only 1 point. Okay, we have to find a minimum element in each row, construct a new matrix subtracting from each, and try the minimum value in its row. For the new matrix, find the minimum element in each column, construct a new matrix called the reduced matrix by subtracting from each element the minimum value in its column. Draw the minimum number of lines, horizontal or vertical, that are needed to cover all the zeros in the reduced matrix. If n lines are required, an optimal solution is available among the covered zeros in the matrix. If fewer than n lines are needed, proceed to step 3. Find the smallest non-zero element, call it car, in the reduced cost matrix that is not covered by the lines drawn at step 2. Now subtract k from each uncovered element of the reduced matrix and add to k to each element is covered by 2 lines. Return to step 2. As I have mentioned before, there could be some remarks. The first remark is that if we don't want to maximize, we want to minimize problem. To solve minimize problem, we just multiply the matrix C, or our objective function, by -1, and then we will have not maximize but minimization problem. Okay. And it is an example here. Well, in lectures of a professor that I use here, there some examples, tables, figures, and you can see here there is a enumeration of them. I just subtracted some of them to focus on the very important things for our course. So just we skip explanation. What is Machinesco example? We just see the metrics here. So we have for machine or cars or whatever you want, robots maybe, and we have time to do jobs. One job, the first job, the second, the third, the fourth, and so on. So we can see that machine 1 is the best for doing job 2, machine 2 is the best for doing job 1, machine 3 is the best for doing job 3, machine 4 is the best for doing job 1. And it's the problem because we have to choose who will be assigned to the job 1, machine 2 or machine 4. Well, it looks like it's better assigned machine 4, but and machine 2 should be assigned to job 4. But it's just intuition. It's just our considering of this problem. But can we do this by just this Hungarian algorithm? We can try. So first of all, we can find row non-zero minimum. 5, 2, 2, 3. It is something that I already did. So it is, but it was very intuitive. Okay. Then we subtract from all these members, from all these elements, these numbers. So we have here 14 minus 5, it's 9, 2 minus 2, 0, 12 minus 2, 10, and so on. Okay, we did. And then we cut off these lines when we can find zeros. This one, this one. Then we subtract and so on. And subtract here. Yeah. And final solution. So we choose C 4, 5, which now excludes both row 2 and both row 4. So both 4, sorry, row this one, row 2, yeah, row okay, row 2 and column 4, yeah, this one for further use. Yeah. Finally, we choose okay. Therefore, we can find the optimal assignment here as a permutation 2, 4, 3, 1. Okay. And what we see that sorry, 2 here, 2, 4, 3, and 4, 1. Well, it's something that I have found just at the very beginning using my intuition, but it's intuition because, and I can use it because I'm a human, some kind. But what if we have more machines, we have more jobs, and what if it is not so easy to find? What should I do? I should use maybe Hungarian algorithm that is very effective, and we can develop a software to do this. Why is it correct? Why is Hungarian algorithm provides us with such a good answer? There is some ideas. It's not a proof, but some kind of intuitive explanation. So you can see it here. I don't think I should read it, but maybe if you want to watch this video again, maybe reading will be very useful for you. Okay, so I will read just to make sure that it's very convenient for you. Okay, so step one consists for each row and columns of subtracting a constant from each element in the row or column. Thus, step one creates a new matrix having the same optimal solution as the original problem. Step three is equivalent to adding k to each element that lies in a covered row and subtracting k from each element that lies in an uncovered column, or vice versa. Thus, step three creates a new matrix with the same optimal solution as the initial assignment problem each step. Each time step 3 is performed, at least one new zero is created in matrix, and so on. Okay, now we came to the traveling salesman problem. It's the very important problem in this course, so we will discuss it throughout this course from now, and I think we have some maybe discussion at a previous lecture, but maybe just mentioning, but later we will discuss it in more details. The idea is just to find a way how we can go, how can we create a cycle with no intersections to get from point A to the point A, and at the same time we want to be at all at every point, and the sum of distances should be as small as we can provide. There is some information here, so we have lengths here and permutation. Why we need a permutation is very simple. So if we have such numbering, maybe not in this way, 1, 3. The cycle means like this cycle means that we know that we goes from what a point to what another point, and we never come back, and we never, and so on. So if we place here, so our permutation is just 1, 2, 3, 2. Well, where is 4? Sorry, 4 to 4 to 5. But we can imagine, well, we do not have constraints or graphs, just costs. It can be, I'm not sure if it can be infinite, but we will use a situation when they're finite. So we can get from any point to another one. I think we can use finite. Well, we can use finite, but sometimes infinity is also an option. So the permutation, yeah, infinity is an option. Okay, we have this permutation, or maybe we can find this one, and so on. So, and we want to find this. How can we solve it? This problem is known to be NP hard. It's a very difficult one, so there is no polynomial, there's no alpha, such that the solution requires such costs. So we need larger than this. Well, there is a theorem of like NP equals polynomial classes. So, but I would like to avoid this problem. So it is we have no proofs right now of this. I mean, it's open problem. It's very difficult open problem in computer science. and we don't know if these classes are equal or not. So I just assume that they are not equal, as many other scientists, but we don't have any proof. So maybe they're equal, but it will be very, very strange. And we want to, first of all, to connect it with a very applied problem, and just job sequencing problem, GSP. It's not JavaScript, it's just job sequencing. Sorry. The idea is the very simple, that if we have a permutation here for cities, we can have a permutation for jobs. So for example, I have a job one to drink tea, to write an article, to make research, and for, I don't know, something else. And I have to find the way how to make ordering, like drink tea, then uh, create publish an article, then make research and something else. But maybe it's not optimal, because if I have no research, what kind of article can I publish? It will be very low quality article. So I have to drink tea, maybe, then make research, then publish article, and so on. Or maybe I should drink a tea not right now, but later, and so on. So it's job sequencing problem, but it's the same. So we have the cost here of switching from 1 to 2, and we have a permutation here. It is written here to what Hamiltonian cycle. Yes, but I will skip it for this. Okay, sometimes we are almost finished, but we have some time to discuss this thing about branch and bounds. I think it will be a great finish today, to stop at the very beginning of branch and bounds algorithm. So the lower we can get the lower bound for this problem. Let's imagine that we have some graph. Uh, well, graph, and we want to estimate. So what's the time for the line? For example, we have an employer, travel man, and we want to understand where should we wait, where not where, when we can wait him when he will be back. So for example, we want to do some work, and we want to, I don't know, make some repair to repair his office, or maybe we want to clean his office, or maybe we want to go to another building in the city, or I don't know, but maybe many things. And we want to know when. So we have time, very small time, so he cannot get back uh, before this time. There is no way. And another way, he cannot get longer than this time. Um, we can estimate. There are many estimations. The first one, it's not written here. Well, I believe it's not here, but we just find here the shortest age, as we did in one of the previous algorithm. And if we have n cities, we think, and the shortest one is just C1, we say that, well, delta t here is the smallest. Say, okay, t1 is just larger than delta t, like here. Of course, it's not the very good estimation, because maybe it's a very short path, but there are all others are very, very long. So it's not very good. But we can get the same for this one. So two is smaller. We can get it here the longest road. For example, this one. Delta type, for example, and the same. So we can say that the real time from here to here, but it's very bad estimation. But it's something. It's something that we can have. Now we know that we have this time for repair his surface if we need to, and if we don't have this guy at our office, we maybe should call to 911 or another number because something wrong with him. He cannot be there so long. Okay, there are many versions, so we can see that there are n factorial different tours, but we don't want to check all of them. We would like to cut them. Oh, there is a solution, feasible solution here, so you can see it later. And the guys, so this, I believe the professors at 67, it's very old articles, but it's, for example, Prim algorithms is about 10 years before them. They have found this, and they decided to check and to test how good the algorithm and how good this bounds for randomly generated problems. And even not at that time, but later, they have performed the following experiment. They generated 400 problems with some estimations here, well, some bounds. The costs, it looks like a probability or expectation, so it's more about a probability theory, but they didn't do this probability calculations. They just used some. I think that it can be considered as Monte Carlo method. Or something similar. The idea of Monte Carlo is like a casino. It's very famous, and it means that if we cannot check all variants, we just make a sample. For example, we have to check, I don't know, if, well, let we have a social network and we have people with a property and people without a property. And we want to check if it is true that A always a friend of only A. A man, a person with a property is a friend of a person with a friend with a property A, or maybe with different properties, and but there are 1 billion or so people, and we want to know just some percentage. It's very difficult because there are a lot of such edges. If we don't have Google or some other good servers, it's not very easy to find. But we can say, okay, we can get sample from this, not 1 billion, but just 100 people. And it's not very difficult to check their interconnections and have some result. Of course, there is no guarantee that our result is correct, and even that our result is a good approximation. Monte Carlo is not very good method to guarantee something. It's just more about ideas, or maybe even I'm not sure about approximations. But it is widely used because of its simplicity. We cannot solve this problem for 1 billion. We just can't. So there is, it's not an option. But for these 10 people, we can do this. And it's some kind of first estimation, Monte Carlo idea. Okay, and they found that estimation is very good here. Okay, we come to our last topic, a branch and bound algorithm for traveling salesman problem or assignment problem. Okay, assignment problem is an important one, but I would like to introduce the branch and bound algorithm. Maybe you already know what it is, maybe no, but just to make sure, and we will discuss it maybe during several lectures with some modifications, asymmetrical, symmetrical, and so on. The main idea can be illustrated by this figure. I, I will come back and show you some notes there, but the main idea that we have one variant, one road, just maybe one permutation, 1, 2, 3, 1, 2, 4, 5, 10, 7, and so on. Okay, we have it, and then we try to modify it. It's not. I'm not sure. Well, I cannot say that it's completely in a way how genetic algorithms do. So because there are random mutations, there are mirror mutations, and many other things. Here we don't know. We don't have all these variants of mutations and uh, all other things, crossovers. No, but we can check if we have, we can make some mutations or some changes. Can we change some mutation? For example, well, not mutation, we can change 2 and 5. So maybe we should change, or maybe we should make another change. And we can check if this new variant is better or worse than the first one. And there are some ideas of how we can do this. So there is a tree, it's branching idea, and and it looks like what is new about this. So okay, we have branching, we have brute force. It's just the way how we enumerate all these variants. We still have to check each of this variant. Nothing new. It's maybe even worse than our intuition. But the idea is that we can. Sorry, I will show you. Wait a minute. I believe there is a special. Yeah, here. Special figure here, a diagram that can show. So there is branching, and we can find an estimation, and it looks like if we have two variants, for example, with and without, no matter what is this parameter, it's just a detail. And we say that here we have, for our objective function, upper and lower estimation. For example, here we have upper estimation f1, it's an upper, and this one is a lower estimation. So anything that we can do here is better than this one, and less than this one. And if we have the similar here, now let us imagine that we have that this one is better than this one. So the worst case here is better than the best here. What should we do? We should just cut off this variant, and we should not pay attention to this variant. So whenever we have x not equals a property, we just do not try to check this variance. It's not one variant, it's just a tree of variants, bunch of variants, and we cut off all of them. It's like a bounds. So bounds this one and branching this one. So we have properties and we check. There is an example, and there is also two ways of branching. The first idea is depth first. So we goes from problem to problem, and here we goes here too. Well, we go here too, but here we try to check different. We have one problem, and we change. We make only small change to this problem for initial problem, and then small change to the same initial problem, small change to initial problem, and we have branching here. Another thing that we make one change from the initial problem, then we make another change from that problem, and so on. And these changes are not from the initial problem, but from the previous problem. It means depth first tree. Okay, so we can go back and check. Well, I'm not sure that we will be in time, but we can try. If it's not a problem, if we don't have enough time, we can continue during next lecture. Okay, not here. Sorry. Okay, yeah, it's branching here. Okay, and the first idea. Wait a minute. Yeah, here. The first idea is branching rule, a simple branching rule. In general, we led to the solution of AP, its assignment problem. Contain a subcycle with cardinality k. Cardinality means the number of elements in this set. So the cardinality of the set of cardinality, well, the set that contains exactly 10 elements has cardinality 10. Yeah. And this subcycle there, and we can and all solutions containing it of this subcycle can be performed from the further consideration by insisting that at least one of arcs there must not be in the solution. This can be done quite simply by subdividing the original problem with the cost matrix C into k subproblems. In problems PID is set. Well, it looks like we have a cycle here, but we are not allowed to have cycle, and we have to cut, well, not here, yeah, not that we have here, and we have to check, sorry, here, we have to check which one we should cut off here. Yeah, I believe so. If not, I will update next lecture, but I believe it should be in this way. Okay, so we have a large problem and we subdivide into several problems, smaller problems. It is very important for NP hard problems because when we have like it's even true for polynomial problems. You have like this coefficient, like here. It sums and we can solve it, for example, by 2. Smaller problems with just a smaller dimension, and we find that, for example, what do we have here? It's well, smaller, not here. Sorry. Yeah. Okay. Okay. And here we have, so this coefficient here. Yeah. Because it's 2. It looks like if we divide this problem into several parts, we can solve each part very effective, and then we can sum up, and then we have very great increase in effectiveness. Unfortunately, we cannot do this always. We have to spend more time for branching and cutting off versions, so it's not always true that such splitting will give us a profit, profit, not profit, but a profit. But anyway, we try to subdivide into several problems. I try to have an estimation for each of them, and if we have good estimations, we can cut off, and in this case, we will have an increase. So the idea of branching. Details is shown here. And another thing is a subcycle elimination algorithm, like C. You see there is a very interesting, we now had SPA, we have C. It's about relaxing, though we are now not in a relaxing circumstances because it's COVID and other viruses, medical problems, but good names for these theorems and these terms. And with a simple branching rule. Branching rule has been described before. In general, let the solution to the assignment problem contain a subcycle with cardinality k. This subcycle, it insisting arcs must not be in the solution. Okay, and we have a simple branching rule. We can divide it, and we have bounds. This is very important here. So we not only have problems, but we have corresponding costs, and there is a lower bound of TCP solution to subproblem P1. And this one, so L is a lower bound of the solution. I'm sorry that I'm very fast passing this branching and bounds. We will pay attention to this next lecture. Right now, I'd like to introduce this idea and give you the basic meaning. So as you can see, we have what does it mean? That we put that some costs we assign to be infinity. So we say that we don't want that we can get from 1 to 2, and from 2 to 6, and from 6 to 1. So we not not ask, we make a restriction that our solution should include or should not include these arcs. So we say that our solution should not include arc this one. So you want to do whatever you want, but you shouldn't include in optimal solution this arc. Okay, but we don't use this arc. Then we check problems if we don't use also arc from 1 to 8, from 8 to 2, and so on. And then we have more and more restrictions until we have no enough edges to solve the problem. If we eliminate, well, if we go to the depth, so we can imagine, not imagine, estimate height of this tree. If uh, we know that the maximum number of these edges is n square minus n, so it's the maximum number of all edges. So we assume that there is no edge from the one city to this city, and the height cannot be larger, because if we eliminate all these edges, there will be no edges. And even before this height, there will be too many restrictions to solve the problem. Okay, some problems here, as you can see, some rows here. I'm not sure. Wait a minute. How much time do we have? Wait a minute. I check. Okay, today. Oh, okay. We have 9 minutes. Okay. If you have questions, you can ask me right now, or you can write it, because we have only 9 minutes. And if you have questions, I can try to answer if there is, or comments, remarks maybe. If you don't, I just will go through these slides. So you are free to ask questions or write them. Okay. I assume that you have no questions right now, or maybe you have a plan to ask me later. So it's okay.
Sorry,
Yeah.
will you send the lecture notes to us?
Uh, yeah. Yeah, I will. I will send this file, and maybe the complete file, maybe not these slides, but maybe also a complete file. Yeah, I will take emails from our office. Well, I mean, our Office of High School of Economics, that who has your emails, and then I will send. I think it's like a Yaduk dot hse dot r o, or something.
We can drop the emails here. We
Oh,
are
okay,
we
yeah.
have 4 people here.
Okay. Or maybe later, maybe next lecture, I just provide you with all these materials, with all these lectures, if you want. So,
And also, if you have books,
okay,
all these PDFs, if you can
okay,
share it with us.
okay, I see. Okay. Yeah, I think it's a good thing. I have this lecture. Well, it's about this 10 lectures on computational thing of combinatorial optimization. I can share it. Okay, thank you. Nice.
And also, we need the first lecture which we had last week.
Okay, I see. Okay, nice. Um, Maybe something else, or just only that?
We can write our emails here as
Okay,
as
I see.
so
Okay,
you don't need to check there.
okay, thank you. Okay, so we have a rejection rule. The idea of the rejection rule is just to cut off some costs for solving not important sub-problems of our large problem. We can eliminate subcycles and so on here. And we can redefine lower bound. So it looked, when we have such a tree of branches, it could be that some estimation, for example, we have only 3 branches, and we have there like f, it's estimation, so the lower bound. But later, maybe when we have branching there, we have better estimation. This one, like which is well, it's lower bound. Yeah, like here. And in this case, we replace this lower bound by this one because we found branch whereas the worst solution is better than our previous estimation. And we can use this for the cutting of branches all over this tree. Okay. Okay. The procedure is breadth first, type of search. Breadth means that we check only small changes considering the initial one, and depth means that we have many changes there. Okay, we have an example. I'm not sure that we have enough time, only 5 minutes, but I will just show you and maybe you will get the main idea of this, but it's very short. We are very short in time. So let me have a traveling salesman, a traveling salesman problem with costs like in this metrics. So we have 5 cities, and we know that though we have a permutation, we need to find permutation. For example, the first from the first city, he will go to the city 3. From the city 3, he will go to the city 2. From the city 2, he will go to the city 4. From the city 4, he will go to the city 5. From the city 5, he will go to the city 1, and that's all. Okay, this infinitism, but of course plus infinities, means that we don't allow this person to stay at the same city, to go from the same city to this city. And okay, we have this idea, and we have to change matrices because we want to use arrangement problem as an estimation, and for arrangement problem we use Hungarian algorithm, and Hungarian algorithm is just about for looking for minimum numbers in rows and then subtracting them, and then cutting off rows and columns. So we cut off those where we have zeros. Okay, we did it. We proceed with this algorithm. We find here that we have this cost. Then we eliminate subcycles because when we use a Hungarian algorithm, there could be subcycles. Yeah, they could be, I believe. Okay, and then we have implementation. Okay, and then we have corrected resultant metrics. There are some examples. So we use corrected resultant metrics here. Then we use this one. And then we apply Hungarian algorithm to the second traveling salesman person, salesman problem. Sub-problem for solving assignment problem for the corrected matrices. Yeah. And we get the optimal solution, this one. And permutation is this one. So we should go from 3 to 4, from 4 to 2, from 2 to 5, and from 5 to 1. And there is some kind of, well, here it is an analytical solution, but of course it cannot be solved analytically. Well, I'm sure that it can be solved analytically for the larger cases. Okay, we have only 1 minute, maybe solution tree search principle. Yeah, we have discussed it. Branching leaks. Okay. Oh, okay. We're in time. Of course, I'm a bit worried. So sometimes it was too fast, and maybe not all details of branching and bounds algorithm was were described right now. But don't worry. I think that we will have enough time during February, March, April, May, and so on. So we will have enough time to discuss all details. Please let me know if you have any questions about it. I will provide you with video and lectures. Okay. Today the lecture is over. Uh, we will meet in 1 week. So next lecture will be next week.
Can you read the question in the chat?
Okay. Thank you.